I'm Gisela Ambozero, and I am here to have the honor to introduce one of my best friends, Professor Freeman. Uh, Harold was born in North Carolina, and it seems he completed all his studies there. And then he started, after he completed his BS degree in chemistry, he started to work to Burroughs Wellcome Company. And after 10 years, then he joined North Carolina State University as an associate professor of textile chemistry. So in 1982, he started to work there and was promoted to professor in 1989. 2 years later, he was chosen the first Ciba Geigy Professor of Dyestuff Chemistry. So please, besides all that introduction, I must say that Harold is one of the persons that knows more about dyes that I met in my life. So I'm delighted to present you, introduce you, and also hear your talk. Harold, the stage is yours. Thank you.
Thank you, Gisela. I hope everyone can hear me.
Yes.
Do you have access to my slides? Yes?
I had. Hope everybody.
Okay.
Okay.
So I will start. Sorry, my voice is a little hoarse today. I'm not sure why, but perhaps it'll get better as the presentation goes along. I've been asked to review, let me go back. I've been asked to review a number of papers, manuscripts that were submitted to various journals over the past couple of years, and an increasing number of these papers in the color chemistry field pertain to natural dyes. And I always found it interesting that many of the writers described synthetic dyes as toxic and natural dyes as safe, which makes this particular question associated with my topic, my paper presentation, especially relevant for this conference. I'd like to address this question by starting with a review of key background in this field. With this in mind, I plan to cover the 5 basic or 6 basic points that are covered on slide number 2. I need to remove something from view. Okay. I show on this slide the scope of the presentation. I'll start with some historical perspectives. And as part of the presentation, also cover the basis for color in organic compounds. It is interesting that less than 0.1% of all organic compounds possess color, and there are good reasons for that. And I'll talk about some of them in this presentation. And then cover synthetic dyes and natural dyes structurally and some of their properties. And then finish with a new approach to dyes, especially natural dyes. I think most of this audience will recognize that dyes can be classified in 3 different ways. Most of the presentations that we've seen involve classification of dyes according to their molecular structure. Anthraquinone dyes, indigoid dyes we've seen so far in this presentation, previous presentations, and in this presentation we'll learn a lot about Azo dyes as well as natural dyes. Dyes are also classified based on their end use, and in our laboratory it's the textile applications, and to some extent dyes for for hair and medical applications are important in our research activities. Dyes are also in the textile area classified based on their application, either direct dyes, acid dyes, dispersed dyes. We've seen vat dyes in the presentations that have been given, as well as basic dyes. This slide, this is slide number 4, indicates the factors associated with color. There are 3 main properties that all dyes have. They have the ability to absorb light in the visible spectrum. That's 400 to 700 nanometers. They're conjugated compounds, and we'll talk about what that is. They have chromophores, and we'll also see that they have auxochromes. Take any one of the first 3 properties away and color goes away. So all 3 properties, the first 3 properties, must exist in order for color to be present. Slide 5 indicates the relationship between the color that we see and the color that is absorbed. So we must have a light source, there must be a colored object, and there must be an observer, in this case, the human eye. So we see something as red because the color is blue and blue-green absorbed. If you put those 2 colors of light back together again, you get white light, and so orange and greenish blue colors are known as complementary colors. On slide 6, we see examples of chromophores, another feature of all compounds that possess color, all organic compounds in particular. Most of the dyes that are used in textile coloration, whether they're natural or synthetic, have either an anthraquinone chromophore, and I show that on the top left, or one or more azo groups. There's a small subset of carbonyl type dyes that don't have the anthraquinone group, but there are also nitro dyes that are yellow that are extremely important for their photostability. They're blue and greenish dyes that are triaryl methanes that are especially important in ballpoint inks. Chromophores, even though they're essential, must be part of a conjugated system in order to generate color. And I show the example on slide 7 of the azo group between 2 saturated methyl groups, and the resulting compound is colorless. But if you put that same azo group between 2 benzene rings to give azo benzene in this case, the color is orange. So chromophores and conjugated system must be part of a molecular structure in order for color to exist. There are also auxochromes, referred to as color aiders. They're not responsible for color, but they can influence color, make it brighter, shift it to higher wavelengths or lower wavelengths, give affinity for fibers such as the SO3Na, the sulfonate group, gives dyes affinity for cotton, depending on the molecular structure, or nylon or wool. The cationic NR3 group gives affinity for fibers that are anionic, such as acrylic fibers. The CF3 group enhances brightness. It's an expensive group to generate, but it gives very nice bright colors in most cases. Now this circles us back to conjugated systems, and without chromophores such as an azo group or an anthraquinone group, it's rather difficult to produce color using only double bonds. So we see here examples of conjugated systems, these systems of alternating single and double bonds. And we see, starting with naphthalene on the upper left, it gives absorptions in the UV region only. We need at least 4 benzene rings linked together in order to produce color, and we have naphthacene giving absorption at 460. Pentacene gives a blue color, but that's 5 rings put together. And if you look up the cost of these compounds, you'll see that pentacene probably costs these days about $100 for a gram. And so there's no way we could afford to do dyeing of textiles with a compound like pentacene. There are naturally occurring compounds that are based on these conjugated polyene systems. Vitamin A gives an absorption at 325 nanometers. So the principal absorption, therefore, is in the UV region at the spectrum on the right-hand side of the screen, but it gives a small amount of an absorption in the visible spectrum. So there are compounds that have the principal absorption in the UV region, but a small tail of absorption in the visible spectrum. And so we can get very weakly colored solutions. In the case of vitamin A, this compound that absorbs at 325, we get light yellow solutions. And if we increase the number of conjugated double bonds to 11, we get beta carotene, the structure at the bottom. So we recognize that as the color responsible in carrots, giving carrots their orange characteristic color. Okay, so let's talk a little bit about the direct comparison of synthetic dyes and natural dyes. On slide number 10, we're reminded that the first synthetic dye appeared in the mid-19th century. Malvine was extremely important because it was found that it could dye silk, the regal color associated with Tyrian purple that was generated from snails, and it took about 1,500 snails to produce 1.5 grams of Tyrian purple. It was so precious that it could only be worn by royalty. The second dye, and this is arguably the case, direct red 28, compound 2 on slide number 10, was the first dye or type of dye that could be used to dye cotton fibers without the use of a moistening agent, and was therefore referred to as a direct cotton dye, meaning that there's no need to pre-moisten cotton in order to have uptake of the dye, which was a characteristic reality of the application of natural dyes to cotton. Here are some examples on slide number 11 of the basic types of synthetic dyes that are in the marketplace, starting with the direct dye at the top, a direct black dye that has 4 azo groups going from left to right or right to left. Compound number 1 and number 2 is a reactive dye, a monoazo dye. 3 and 4 are examples of vat dyes. Number 4 is indigo, so we've talked about that in this conference so far. Does not have good wash facets, very important for dyeing denim, but washes out relatively easily. If you replace it with the blue dye number 3, This VAT dye has two anthraquinone groups linked together. VAT group 4 has very good wash fastness and light fastness and bleach fastness for that matter. And then 5 is a dispersed dye, looks a lot like a number of the anthraquinone natural dyes that have been discovered. 7 is an acid dye for wool and nylon fibers, and then 6 is a sulfur dye that has very good wash fastness, but bleach fastness is not good. Much of the work that involves the environmental chemistry of dyes has been developed in parts of Brazil, especially Sao Paulo, and is the work of Professor Gisela Bezerra, who did my introduction. She's done some very nice work on the identification of dyes that end up in the Castaias River. Starting, this is on page 13, in the upper center of the slide, we see a dyeing processing plant, and this is a plant that specializes in the coloration of polyester fibers. And at the end of the dyeing cycle, the wastewater from the dyeing process is transferred to the river, which leads downstream to a waste treatment plant, the orange box that we see towards the bottom of the screen. This water that's taken into the plant is treated, often with chemicals such as molecular chlorine to chlorinate, purify the water, and then the water is released to the drinking water areas for an adjacent town. And so one of the key questions that needed to be answered was, what is the state? What is the nature of the water that comes out? Is there any toxicity associated with that water? Water was therefore sampled, as we see on slide number 14, taken to the laboratory where a number of extractions were taking place on the alkaline, neutral, and acidic side. And toxicological assessments were carried out, in this case, mutagenicity of the water from different spots was characterized, and it was found that water that ultimately leads to drinking water was mutagenic, and at least 2 strains of Salmonella typhimurium bacteria. And so that really caused the ears, certainly of regulatory agencies, to perk up with the recognition that something needed to be done to the water that was being released as a discharge before it could be used as drinking water. Now, much of what we know about the toxicity, or I should say the true concerns associated with synthetic dyes arise from Azo dyes. Otherwise, this would not be a story at all. Indeed, the dyes that were detected in the Castaias River were Azo compounds that we talked about earlier, have the characteristic nitrogen-nitrogen double bond. These dyes are extremely important because they have high tinctorial strength. You get a lot of color to the pound of a dye. They're easy to make. It's manufacturing plant, and I'll talk about this a little bit more in a minute. They cover the entire color spectrum, everything from yellow to blue to brown, black. They do have some disadvantages though, and this is really the main reason the question exists. Are natural dyes better, presumably meaning better than synthetic dyes? That some of these azo compounds are based on genotoxic aromatic amines. This slide 17 is important because it shows that there are two specific reactions always associated with the synthesis of an azo dye. There's a diacetization step where an aromatic amine is treated with nitrous acid to give a diazonium compound. The diazonium compound then interacts with some type of coupler. Paraquisol is shown in this example, and that gives a diazo coupling reaction to produce in the bottom left a typical monoazo dye. That means, as we see on slide number 18, that we can look at the structure of any dye and do what's known in mental chemistry a retrosynthesis process. So anytime we have an azo dye, we can look at its structure and know the precursors that were used in the manufacture of the dye. And in this example, direct red 254 has two azo groups. That means two diazo couplings were used in the synthesis. And we can see by splitting the bonds associated with the generation of the diazo compounds that structures A, M, and E were used in the synthesis of this dye. So it's always easy to know which aromatic amines were used in the synthesis of the dye by doing this simple retrosynthesis process. We also know, as shown on slide 19, that azo dyes can undergo reductive cleavage, and that's the splitting of the azo bond, this nitrogen-nitrogen double bond. Mammalian systems, such as the human body, have these azo reductase enzymes, and as a result, a dye such as Direct Black 38 that was used quite a bit in printing, especially on paper, the daily newspaper, often involves printing of the text using Direct Black 38 until it was determined that this dye was based on an aromatic amine that had been established as a human carcinogen. And the arrow in the middle of the screen points directly to benzidine, which is known to be a human carcinogen. And as a result, Direct Black 38 was banned from the marketplace. And so the point of this is that really it's the azo dyes that were the subject of concern because of the potential for them to undergo reductive cleavage by reductase enzymes to produce aromatic amines that may or may not be mutagenic or carcinogenic. In 2002, there was a German ban imposed on any products, any commercial products containing dyes that were derived from any of a group of 20 aromatic amines. And I show the aromatic amines on this slide and the next slide. And so the idea was that if you had a product in the marketplace derived from any of these 20 aromatic amines, there was the potential that the dye could be ingested into the body and then metabolized to these harmful amines. This was a big deal because, as the right-hand side of the slide number 20 shows, aromatic amines can undergo N-hydroxylation, and that hydroxyamine undergo acetylation followed by elimination to produce nitrinium ions, these N plus species that react in DNA, and that process could lead to mutations of DNA, which is believed to be the step leading to carcinogenesis. Here on slide number 21 completes the aromatic amines that were part of that initial ban in the EU directive. Okay, so now natural dyes, starting on page 22, and I couldn't resist this picture of one of my favorite movies called Braveheart. I'm a big William Wallace fan, who was the star of that movie. But I took this picture and included it because his face is painted with woad that we learned earlier contains indigo as a significant component. And so we start here with just a brief review of natural dyes. We know that they're available from plant or animal sources. They can differ in the concentration of actual dye that's present. And it's interesting, I put this note towards the top too, just a reminder that if we were to move over to natural dyes completely and not use synthetic dyes any longer, it would take at least 100 million tons per year of raw materials to satisfy the total need for dye worldwide for various applications, especially textile application. One of the things we also know about natural dyes is that they're not single components for the most part. They're precisely defined, and this can be influenced by the environment, the land, the temperature associated with the growth of plants, for example. So we can't count on getting the same dye from region to region, and we'll come back to that thought a little later. But this fourth bullet point on slide 22 is really important too. Even though we try to use these dyes for textiles and develop methods, it is important to recognize that nature did not develop its dyes with textiles in mind, unlike synthetic dyes. This last point is important from an environmental standpoint, because it is true that these dyes have very good biodegradability, unlike synthetic dyes. On slide 23, it's a reminder that in the beginning of textile dyeing, though, all of the dyes were natural. Some were from animal sources. We talked about Tyrian purple that was used on silk, kermes, cochineal, and show at the top, which show the animals, the natural sources, and at the bottom, fibers, fabrics, textiles dyed with that particular dye. Some more examples. We had a presentation earlier about well and the wonderful yellow color that it produces. Indigo, after some buildup, gives a nice blue on cotton especially, and then madder gives a beautiful red color on silk and other fibers. And then the structures, vat blue 1, natural red 3, indigoid, anthraquinones, polyenes we talked about, such as beta-carotene and lycopene. Flavonoids, very important for their fastness properties, and then chlorophyll, the natural green 3, chlorine type magnesium complex. We've already seen that for the dye application process for natural dyes, there's a harvesting component, an extraction step, whitening of the textiles, and from time to time a rinsing step just before the dye is applied. There needs to be a moistened in most cases, except for indigo, in order to get uptake. And this has been discussed that in the case of cellulose, there is now this linking of the dye to the fiber with some type of moistening agent. Is often a metal such as aluminum or iron. This is a bit of a summary slide, just thinking about what is the case for the two dye types. We can say, as shown on slide 28, natural dyes are renewable, biodegradable. They're perceived, and I'll leave it at that for the moment, to be non-toxic. Indigo is by far the main survivor of the initial use of natural dyes, especially on a textile industrial scale. On the other hand, synthetic dyes are stronger, much higher tinctorial strength. They tend to be brighter. They have better fastness properties, more economical, and as a result, more profitable. This is an important slide too, slide number 29, because it reminds us that the dyeing efficiency for synthetics is better. Reproducibility of dyings from region, from country to country is better. There's a better slide range, a shade range, sorry. And the toxicological properties are a bit clearer. A lot more work has been done in this area than on natural dyes. And on the right-hand side of the slide, I indicate a typical shade that you would get on cotton and wool, which means you need about 2 grams of dye, 100 grams of fiber. And I point this out because it means that for a natural dye, you'd need almost 300, up to 300 grams of the dry plant in order to produce shades like this on cotton and wool. So that's important. Keep in mind. And then there's the land usage consideration. If we think about the amount of synthetic dyes used on an annual basis, about 400 tons of dye. And so with indigo as an example, we need 0.3 of a square mile per ton of indigo. And the amount of fresh dye plant, 176 million tons is the most recent number that I have seen. And as a result, about 1/3 of the world's agricultural land would be used. And the idea again of this slide is if we were to shift over to natural only, this gives us a feel for just how much land would be required to generate the amount of dye needed. One other thing that's important, I've really talked about the essence of this slide, the dyeing process is 2 steps, and the fact that in this middle section here that weather and seasons influence the availability of natural dyes. A little bit about the cost, and the main point of this slide, number 32, is that there's a much higher cost associated with the use of natural dyes versus synthetic dyes. We started to do some work in Professor Umbezero's laboratory to have a better look at natural dyes, especially the anthraquinone dyes, and here are some examples of dyes that she's been studying more recently. Dermarubin and its chlorinated derivative, dermocybin, Emodin, and the purities of the dyes used in her toxicological assessments are shown, so very pure samples. And it was shown that Emodin is mutagenic. The other two dyes are not, and so that's an important thing to keep in mind. Another important point was for the evaluation of these dyes, especially the anthraquinones, it's helpful to use a bit higher concentration of the S9 homogenate in order to do the pre-activation of the dyes in the mutagenicity test. So you get better results from increasing the concentration of S9 associated with this study. We also found that TA1537 is an important bacteria strain to use in these studies, and I think this strain has been downplayed a bit as time has gone on, but now it's coming back to the forefront as an important strain in the assessment of the mutagenicity of compounds, especially of the types involved in this study. And so this slide maybe should have gone first, because it does show that Emodin was mutagenic, the other two not. It's not entirely clear from the open literature whether the glucoside derivative of Emodin is mutagenic. We found that it was not. In terms of aquatic toxicity, looking at Daphnia as the species used, a substance used in our testing, that there was a low level of toxicity associated with aquatic toxicity, acute toxicity associated with these compounds, not enough to discourage us from continuing to use them in our studies. And so if we were to stop here, I put conclusions with a question mark. We would probably assume that certainly natural dyes as well as synthetic dyes are here to stay. The key thing is that synthetic dyes don't require land, even though they're not biodegradable. The properties, fastness properties are superior, color strength is superior, but the fact that they're not biodegradable, and that's by design. They're designed to withstand exposures to washing, to bleaching, to ozone in some cases, and to chlorine in some cases. One might say that natural dyes, synthetic dyes have an advantage over natural dyes because of the fastness properties. But as Paul Harvey, the late Paul Harvey would say, now the rest of the story. And the idea is that the development of dyes from microbes will influence the answer, I believe, that we give, let's say 5 years from now. And we've seen microbes grow on bread and cheese and other products. But it's only been in recent years that we've thought about the possibility of taking advantage of how these dyes these colorants are generated and make natural dyes equally important in terms of their uses as time goes on. So the point of this slide number 39 is that the microbial world is colorful. We see melanins in air, carotenoids, flavonoids, anthocyanins, anthraquinones, and a wide variety of colors, as we see at the bottom from mushrooms, from yeast, from bacteria, from mold. Just an amazing world of color associated with microbes. We also know, as shown on 40, by the way, if you're wondering, I am coming to a close. I'll be finishing up very shortly. We know a lot about the genes associated with the biosynthesis of dyes, such as carotenoids, shown here, that these genes have been sequenced and used to produce carotenoids, as shown on this slide, so we can generate pure samples of beta carotene, lycopene, and others of various colors. And so here are some examples of the use of gene sequences to generate colorful natural dyes in pure yields. And so this is part of the branch of science known as synthetic biology. And these genomes, we hear a lot about genomes in the medical field, but there are data sets available in the open literature of all kinds of living things, including the microbes that we've mentioned. And as a result, it's possible to synthesize pieces of DNA that can be used for our purposes to generate dyes. We can design the colors that we want by building the right types of cells. Production can be efficient, can be scaled up in reactors. I'll show that on the slide that follows. And this can be done at ambient temperatures and pressures in the absence of catalysts, especially toxic catalysts that have been historically used in the generation of anthraquinone dyes, and is one of the contributing factors to efforts to replace anthraquinone dyes with azo dyes based on heterocyclic amines. This is a slide that probably could have number 42 placed earlier, and it's just a reminder that the colorants that are produced by these microbes are photoactive. They do get absorbed by the human eye or light coming from them, interact with rhodopsin, the component in the cones that are in the back of our eyes, that have these types of structures shown on the right that influence their changes in conformations will influence the colors that we see. And here are some examples, again, some other examples of dyes produced from microbes, similar to the dyes that are in plants, and we see a variety of cyclic and acyclic compounds, including anthraquinone and flavonoid type structures. And this is, I know you can't see this slide extremely well, but the idea here is that biosynthesis pathways for a lot of aromatic compounds have been generated, and genes associated with these pathways have been identified and characterized, and this big group of structures that you can't see on the right, clearly on the right-hand side of slide 44. In the middle of it, it shows indigo. We see quercetin, we see gallic acid, various natural dyes that are well known, the flavonoids generated here. And so the idea behind this is that this is not something that's just in our imagination. The biosynthesis pathways have been established. And the idea of scale up I mentioned is reasonable, particularly because high pressures, high temperatures are not needed in order to produce these colors. So it's an exciting, and the real conclusion, I think, now shown on this final slide, that microbial color production eliminates the need to extract pigments, no land usage, no coal tar-based precursors. Production can take place year-round, no growing season, so to speak, and a number of renewable raw materials are available and can be used to produce these microbial-based colors. I'd like to thank some of my colleagues, these three in particular, for helping with this presentation and for teaming together as part of the BioColor program to introduce what I believe is going to be a really interesting next wave associated with natural dyes that will be entering the marketplace. Thank you very much for your attention. Questions?
Right, we've got lots of questions.
I hope I have some answers.
Right, let's make sure, oops, everybody can talk. I want to make sure you can talk. Right, there we go. Let's move down through here. Donna?
Hi. Very, very interesting. And I'm wondering if you've, I did not see the genus Actinomycetes up there for color, because there's quite a bit of strong color in there. Have you seen them or tried them or know about them?
I have not tried them, and this was just a small sampling, as you're pointing out, of what the possibilities are. So I didn't intend to exclude them.
Okay, so then you know, this is so exciting because I do work in a laboratory with those microorganisms, and I've been getting a collection of all the beautiful colors, and so I'd like to somehow work with them and do a project. I mean, it's just my next step in my dream to carry on.
Yeah, we'd love that. Have you isolated any of the dyes? That will be an important step for us too.
No, I've only just imagined the possibilities because I'm not a chemist, I'm a microbiologist.
Right.
So that would be something I'd have to work with collaboration.
Yeah, we'd love to do that.
Exciting prospect.
Mm-hmm. Yes, absolutely. It's a smooth fit with what we're trying to do.
Right. Yeah, and I've thought about it for like a couple of years. Oh, if I could only get the dye out of this.
Brilliant, brilliant. Okay. Fascinating question. You'll have to go and chat to Harold later, I think, and
I sure will
explore possibilities. Wonderful.
Thank you.
Okay.
And also Professor Razanen, Rika Razanen, who gave the opening presentation, she and Professor Bazira are collaborators with me. So it would be great if we could have perhaps start out with a Zoom connection and just talk through some of the possibilities.
Sounds great. Thank you.
It's really exciting. Really exciting. It's what this program today was partly about. Meeting up with people, and yes, excellent. Who we got here? Is it, I'm trying to see who's which. Oh, Joe, your hand's up.
Yeah, I think it's brilliant and really interesting to see that you're using bacteria and biothings. My only concern is that, again, you're talking about using raw materials from plants. Now, in the UK at the moment, with the biodigesters that we have, a lot of raw materials that should be going back onto the land to fertilize it are not being, they're being shifted sort of on, tractors are doing 60-mile round trips to feed the biodigesters. And that would be my biggest concern about using bacteria again, is actually providing the food to feed them. I understand completely about using natural plant-based dyes as well with this. But we need to start looking more, in my mind, at as an agricultural person as well, at the actual economics of that side of it. Because I don't know how much food you need to put into them to get the dyes out.
Yeah, that's an excellent point, and I don't know that answer either, but you're right.
I think the situation.
There's more to the story than just producing the color.
Indeed, I would say we need almost to do a kind of soft systems analysis on this and have a look at the whole system with the what we call the environment, all the external factors, and just see what would be the weak points and how we'd address them. I talk about that because I've done it for looking at anaerobic digestion, making biogas. So I've done a little bit of that. We've looked at the whole situation, although in theory it looks fantastic. There are huge gaps in the system where it all falls down. I think Joe may have highlighted one here. Anyway, I think it's absolutely fascinating. Right, we got somebody was behind me waving a hand. There we go. Who we got up here? Belle.
Thanks very much. Thanks so much, Professor Freeman. That was really fascinating. Yeah, I'm really intrigued by the whole world of color from microorganisms, and I'm just so looking forward to seeing kind of where that goes in the coming years. I have a comment and a question, and my comment kind of picks up on the points that Jenny and Joe were just making about a more kind of holistic mindset when looking at the relative impacts of synthetics versus natural dyes. Because I was thinking in your on your slide when you were talking about kind of the quantum of natural dyes and the land that would be required to replace synthetic dyes. For a lot of us who are interested in natural dyes, like we take a much more holistic approach to our ecological concern, and we don't see the level of current textile production as being even remotely sustainable, regardless of whether synthetics or natural colorants are being used. So the math will be quite different when you start looking at reducing the fast fashion industry and its overall ecological and, frankly, human rights impacts. But my question is related to kind of costing or looking at the ecological and human health impacts of the entire supply chain of the production of synthetics. Because I find that often in discussions with people about synthetics versus naturals, synthetics only ever seem to be sort of addressed in the downstream part of their existence. And I'm wondering if you've looked at ecological and human health impacts of the entire supply chain in terms of the ingredients that are required for the production of synthetic colorants, including the role of the fossil fuel industry.
And that's a great point. We have not done that, but it's known, and a big part of what was done goes back to the aromatic amines used in the manufacture of Azo Dyes. Azo Dyes comprise at least 70% of the synthetic dyes that are in the marketplace, and much of the work that has been done upstream, as you're describing it, involves looking at raw materials, the precursors for these dyes, both the unit reactions associated with their manufacture, the sulfonation, hydroxylation, nitration, halogenation reactions. And as you point out, when you think about what has transpired, particularly over the last 10 years, that it is not going to be sustainable to continue to generate the raw materials that are needed, much less deal with the manufacturing of the dyes themselves. We know that to be the case because of the difficulty in identifying and finding sources of some of the raw materials for the historically very important textile dyes. So from the standpoint of the environment, as well as the availability of raw materials, it becomes clear that we need other solutions that perhaps in combination will allow dyeing to continue to take place. I shudder to think of a world without any color.
Me too.
I'd like to say a very special thank you to all of our speakers, especially the last one. Let's turn around and face the right way. It was headlined or straplined as Where Craft Meets Science. We had a lot of craft in the first part and some science. We've certainly had some science at the end. Thank you very much, Harold. That's it rounds us up really nicely of all the talks for today. They've still got some of those lovely kiosks. We should have a little bit of time to do that. It says notices and prizes. Well, it was that was if we had any. I think everybody needs a prize for actually attempting this. And I'd like to thank you all for all your contribution and being here. We ended up a rather reduced number because the technology is a little bit new to most of us. And those that weathered the idiosyncrasies of the screen projection, I think you've mastered it there, Harold. That's very good, and Joe also, and there was one or two others who seemed to get to grips with it. Thank you so much. Thank you to Jonah, our videographer. We hope we've got some nice pictures of what we've been doing.
Absolutely.
That'll be lovely. And I think we'll meet again back in the the team suite where all the offices are, and do go and nab one of the speakers or whatever if you want to go and ask them more and have a look round. We've got 1 or 2 offices or kiosks in there who have the people who have put something in there for you to look at, which haven't actually featured on the stage today. We've got Deepak sitting down there with his in natural dyes, and we've got Everly Yarn. That was Yana, who didn't quite manage to make her booking, and if we'd known it was going to be as difficult to get in as this, I wouldn't have put a limit on it, because I think we probably would have accommodated anybody who wanted to come, who could come. But never mind, we live and learn. This was a pioneering adventure after all. So we will see each other back in the team suite. Thank you very much again, all of you.